Okay, so in the last video, we looked at how to find the optimal point in a valid region, and we did that by evaluating the objective function at each vertex. So you can see here's the example, and you can see the different vertices in our valid region, and our objective function was 2x plus 3y, and you can see we've just put the points into that to get the value, and from that we could see that the point 1, 5 is going to be our optimal point. Now, I'm just going to look at a different method today called the moving line approach. And it's slightly more dynamic. It gives us a bit more flexibility, and certainly it's necessary if you're aiming to do more complicated problems. So I'm just going to demonstrate how that works. Now, I've set up the valid region already here in Desmos. And I'm just going to put in the objective function. So it was 2x plus 3y. And let's make it equal to a value. So that's going to be the value of the objective function at any points. And so you can see when you do this in Desmos, I've added C here. That's going to give me the option of adding a slider. So I'm just going to add a slider for C. And you can see my objective function comes in and I can move it around. Now, I haven't made my bounds high enough. So what you can do with your sliders is you can click on the numbers at the end there. I'll just put a slightly bigger number in and see what happens. So anyway, what you're getting here is the objective function value going. So like, for example, if I stop right there, you can see like along this line, if I put the point, looks like about one for x and 2 for y, that's the value of the objective function there. And so we can sort of go along, and that would be the same as if we put 4 for x and 0 for y. And so we can just sort of move along. And you can see as it's going up, remember we're trying to maximize, as it's moving outwards away from the origin, the value of this function is going up and up. So as we move up, say I hit another vertex over here in the corner, over there, about 4, 2, that is actually going to have a higher value than when we pass through, say, the vertex 4, 0. And we can verify that because you can see 4, 2 has a value of 14 and 4, 0 just has a value of 8. Anyway, what we can do, though, is we just keep sliding out and we follow our objective function out. So you can see the line is moving, hence the moving line approach. And we just keep going out and out until we find the point that is the last one we strike before we leave the we leave the valid region. And there it is right there. That is the highest point available, and that appears to be 1, 5. And if we go back to our worked example from before, there it is, 1, 5 gave a value of 17, which was our optimal point. So that is a really helpful and very fast way of finding the optimal point. You don't have to evaluate all the different vertices. You literally just put it into Desmos, set up your objective function, and slide out until you find that optimal point. Additionally, this is actually really helpful if you, say, are constrained by having to have integer values. So I'm just going to change the one of the constraints here, just to change the valid region slightly. If, for example, we were asked to find the optimal point here, it looks like right now it's sort of at the top somewhere there. But if one of the constraints was that it had to be an integer, that wouldn't work because you can see that's not sitting on one of these main integer lines here. In fact, I'll just remove those minor grid lines for you. There you are. So we're going to need to find points that actually are on those grid lines. And so by using the moving line approach, we can actually find which integer value is the last one passed through before we leave. And actually it appears to be 0, 5. And so that's nice because it's on the edge there. But sometimes what you might find, and again, if I just change this to 4.8 or something like that, so we get some slightly more unpleasant values. In this case, those points out here, none of those are actually valid because they're not integer. But the last integer point is actually inside the valid region. It's actually not on the edge of the valid region. So in this case here, our optimal point would appear to be 1, 4. So again, it's a different type of problem, but you could only solve this one with the moving line approach. It wouldn't really be practical to try and solve it by evaluating points if you were forced to have an integer, because it would be very tricky to work out which integers to test. So anyway, that's the moving line approach. So in Desmos, you just set up your inequalities here, type in your objective function, making it equal to a variable, get your slider, and just slide your way to finding that optimal point.